All right. Thank you for coming. Happy Tuesday. Some announcements for you. First off, there's a math colloquium coming up tomorrow. I've got a flyer over here. It's tomorrow in Galileo 202, so upstairs, but not the big lecture hall. It's the one right next to that one. Um, and it's someone from UC Berkeley talking about asymptotic dimension for what does it mean for the Euclidean plane to be two-dimensional. So if that sounds cool, um, tomorrow, 1:30 in Galileo 202. The other announcement is that Tech Lab has a meeting tonight. There will be pizza and we'll go over some LeetCode code problems. And it's a student-run club that is just here for people who like tech, computer science majors, data science majors, or people minoring. So it should be fun. And there will be pizza. Reminder for you is that the math packet is due this Thursday, so next class period. If you have it ready now, I can take it now. If you want more time with it, that's up to you. Again, hard copy, soft copy, either is fine. Yeah, up to what you and your preference for turning that in. Homework 3, which is the one for this chapter, is tentatively due next Thursday, March 6th, which I'm also realizing is the day of our exam. So I can hear arguments if you want to push that. But that's what it is for now. We will have an exam next Thursday. My plan is next Tuesday will be a review day. I'm hoping we'll finish up this chapter by Thursday, if not today. So that sets us up well, just so that we can have a firm hold on all of the definitions and everything going forward. That's the purpose of the exam. Currently it's like define a graph, draw a picture. What's a cycle, which we'll learn about today, draw a picture. Or some things like in the packet where there are X graphs with Y vertices with some particular property, draw all of them. So something like that should be fairly straightforward. There may be one or two proof questions, but you should be well prepared by the time we're done with this chapter. So make sure to study the notes and read the book. And if you do that and you can recite those from memory, you'll be fine. But again, I'll plan to do a review session next Tuesday. I should have done this before. I've got the homework. On Canvas. I didn't write it on. Okay, so the grades on Canvas. Let me know if you have any questions about that. And we'll go ahead and get started. Let me scroll through. So last time we talked about subgraphs, where we pick some vertices or edges that we want to take from an original graph, and that's our subgraph. We can have an induced subgraph if like the vertices we choose and then all the edges that are incident with those vertices in the original graph get chosen up as well. That's an induced subgraph. We talked about degrees being the number of edges that are meeting at a vertex. So the number of edges that are incident with that vertex. A degree sequence is where we list them all, starting with the lowest, so we list them in increasing order. Then we looked at a theorem 2.1, the handshaking lemma, which is in any graph, the sum of all the degrees is going to be equal to 2 times the number of edges. And so we proved that where every edge has 2 vertices. And so when you sum for the degrees, every edge gets counted twice. That's the way we understand that one. And I think that's where we stopped. Okay. So now we get to talk about paths and cycles. So paths and cycles. And we've talked about this a little bit in the first unit where we look at like what's the shortest route between here and target, or what's the how can we find the amount of current that goes through some electrical network or some amount of water that goes through a pipeline network, or what's the fastest way through a maze. These are all things that we're looking at paths. And so now we're just going to apply some terms to this. So first we need to talk about a walk, where a walk is some succession of edges in a graph. So for example, we can have a graph that looks like this. So I'll start U, V, W, X, Y, and Z. So maybe this is a subgraph of something. I don't really know. But this graph is however long it is. So maybe there's some more vertices between X and Y. But the way we write a walk is a succession of edges. So either we can say, if we start at U, we can write, it's a succession of edges. So we'll write UV and then VW and then WX and so on. And then ending with YZ, right? Just a succession of edges. Another way to write it, instead of writing it all out with spaces, is you could just smush it all together and say, here are the vertices that I visit on this walk. So U, V, W, X, maybe more there, then Y, then Z. That's a walk. Okay, let's draw another graph. We've got U, we've got V. Maybe I should draw the edges first. Terrible edge. Let's redo that. Okay, U, V, W, X, Y, and Z. So this is our graph. And we can say that I've got a walk, which is U, V, W, X, Y, W, V, Z, Z, and then ending at Y. So that's my walk. Let's draw it out. So I start at U, and then I go to V, then I go to W, then I go to X, then I go to Y, then I go back to W, then I go back to V, then I go down to Z, take the loop, and go back over to Y. It's a walk. You know, you're going around the graph, visiting vertices. Um, this is a walk. Something you may notice is that we can repeat vertices and edges as necessary. So like we visited V a few times, W and Y, all those we went to multiple times. Additionally, like the edge between V and W, we went over multiple times, and that's fine. That's fine in a walk. If we want to restrict it in some way, we can do that. We just call it something different. So to restrict it, we can say the trail is it is a walk, but there's some restriction added on. But all edges are different. So all of the edges are going to be different, but I'll say, but not necessarily vertices. So all the edges have to be different, but we can visit same vertex a few times if we want. So an example of a walk, let's make it light blue, or a trail, could be something like, I wrote down U, V, Y, W, X, Y, Z, which is if we start at U again, we go to V and maybe down to Y, and then W, X, Y, and Z. So we visit Y multiple times, but we don't take any edges twice. Like we don't go back up the YZ route. So all the edges are distinct. That's a trail. We can further restrict it. So if a trail is where all the edges are different, but not necessarily the vertices, we can restrict it to say edges and vertices have to be distinct. And we call that a path. So a path is a walk, but all the edges and all the, you can have room there, vertices are different. So we can't repeat. So the situation where we repeated Y, that's not going to fly this time. So let's look at another example. Maybe I'll make it orange this time. So an example of a path could be just from like U to Z, Z to Y, Y to X. Right? So we don't repeat any vertices, we don't repeat any edges. That's a path. So there's a lot of terms here that I always get confused on, where we've got a walk, we've got a trail, we've got a path. Typically, the only one you'll see people actually care about is a path, but as always, there can be exceptions. So path is the one that you'll typically read about and care about, because we've gotten to a level of specificity that works in general. just to note that, like, if we use like the subset notation where we can say that the specificity is in, so over here we've got more restrictive and then less restrictive. Where a walk is just like any succession of edges, I don't care. Repeat what you like. Where path is like, no, no repeated edges, no repeated vertices. The previous problem would be the bridges. The bridges of Königsberg. Yeah. I forgot the exact formulation. Okay, so this says devise a walk through a city, but that crosses each of those bridges once and only once. So no repeated edges. Or yeah, if you consider the island, like the land, to be the vertices and the bridges to be the edges. Yeah, kind of, because the graph has the multiple edges. So the definition don't quite apply because yeah. Yeah, so I guess it would technically be a walk. But a walk where we say don't repeat edges. Or no, it would be a trail. Yeah, I was wrong. Yeah, it's a trail. Okay. So now I think we've got pocket problems 12 and 13. 12 is, let me bring that up if it's open. 374. Well, so yeah, so it gives you a walk and it asks which of the term applies, sequence of vertices, which of the terms apply, and how long is it? So how many edges are there? And where does it start? Where does it stop? Right, did we get an answer for A? Yeah.
Trail, and I click the link for the stakes, and there's between X and Y.
trail length 6 between X and Y. So X, Y to Z again, and then to V, and back to Y. Yeah, so no edges are taken more than once, so that makes it a trail. 1, 2, 3, 4, 5. 1, 2, 3. I think it's length 5. Am I
I thought
am I wrong?
circle was taking place.
So it's Y, Z, Z, V. So we go from Y to Z, and then Z back to Z. Because of the way we write it, where I think the alternative way to write it would be YZ, that's this edge, right? And then ZZ, and then ZV. Yeah, so the loop only gets taken once, and then yeah, and that brings us to 5. If we had taken the loop twice, then it would not be a trail. Okay, so length is 5. I'm gonna erase the drawings over here so we can do the next one. Someone want to give me B? Sure.
So half of X3, which is U is
U and Z. So start at U, U's over here. It's always so hard to tell the difference between U and V in math script. It's annoying. U to V, V to Y, Y to Z. No edges repeated, no vertices repeated, so it's a path. And we take 1, 2, 3 edges, which makes it a path of length 3. There's something I wanted to mention for this one. Oh, a walk is also technically okay because of this, like, the amount of specificity. If we had called both of these a walk, that's also technically correct. But when we are trying to describe things, we'll tend to use the most specific term that we can. So while walk is technically correct, I would prefer path because that's a more descriptive term to apply to, and it tells us no edges are repeated, no vertices are repeated. Okay. I'll give you a second if you want to try and write down all of the paths between S and Y here. Let me see, how many do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9. I have 9. You can separate it by length if you want. All right, does someone have a path of length 3? Sure.
S T Z Y.
STZY, STZY. Yeah, that seems like the shortest path possible. Anybody have one of length 4? Yeah. SVTZY, SVTZY. Yep. Should be 2 of these guys. Yeah.
S T C.
STZXY, STZXY. Yeah, so go across before you go down. Yeah. 5, I've got 3 of them. You just got one of length 5. Go for it.
S E T C.
SVUTZY. 1, 2, 3, 4, 5. Yeah. Anybody else have another one? Yeah.
S T Z W X Y.
STZWXY. Yep. And there should be one more. Guys, view, we've got STZ.
S T Z X Y.
Wait, sorry, I got confused. Say it again.
S yeah, S V T Z X Y.
SVT 2 Z 3 X 4 Y 5. Yeah. All right. Length 6. Yeah.
S V T Z W X Y.
S to V, V to T, T to Z, Z to W, W to X, X to Y. Yep. There should be another one. Yeah.
S V T C X Y.
SVUT 3 Z 4 X 5 Y 6. Yeah. And there's one of length 7. Anybody got it?
S V U T Z W X Y.
SVUTZWXY. 1, 2, 3, 4, 5, 6, 7. Yeah. Hooray, we did it. All the paths. We did all the paths. Okay. So we're going to learn a new definition to work with the next one. So we're going to have a definition of connected, where we say that a graph is connected if there is a path. So now that we know the word path, we can apply it to this definition. Between each pair of vertices. So a graph is connected if there's a path between each pair of vertices. So any pair in the graph, it's connected if there's a path between those. So let's look. There's another definition I want to put here. Bridge. We can say that something is, let me write that again. Disconnected otherwise. So that means that if there is a pair of vertices for which there is no path between them, then we say the graph is disconnected. So let's look at a graph. We've got edges going this way. Is this graph connected? It is, because for any pair, any two vertices in this graph, there is some path between them. There's a way we can reach one from the other. It's all it's all connected. This is one of the ways where there's like a specific definition of like for any pair, there's a path. But it's also intuitive where we can look at this graph and say, yeah, it's all one piece. It's all connected. And there just needs to be a path. We don't care about what the path looks like. There just needs to be one. We can say that something is a bridge if, or specifically that an edge E is a bridge if E's removal leaves a disconnected graph. So if it leaves the graph G disconnected. So a bridge, for example, so this is a bridge, the edge in the middle. Currently it's connected, but if we remove it, then now we have a disconnected graph where like this vertex and this vertex, there's no path between them. There's no way I can get from the one on the left to the one on the right. There's no edge that I can take that will get me there. So a bridge is something that's like us anticipating. If this edge were to be removed, then the graph would be disconnected. So we've got a connected graph, we've got a connected graph with a bridge. And let's look at another disconnected graph. Where in one, we've got a triangle, in another, we've got a path of length 1, and another, we've just got a single vertex. If this as a whole is the graph, then we say G is disconnected. If just the graph was just the triangle, or just this path of length 1, or just this vertex, then we would say that each of those individually are connected. But taking these three components as a whole graph, we say G is disconnected. And these individual pieces, the disconnected parts of the graph, those are called components. So for a connected graph, for this one, there's only one component. For this connected graph, as it is right now, there's one component. If we were to erase this edge, then there would be two components. So the number of disconnected structure, the disconnected structure, that's called a component. Or no. I'll say a component is a connected structure. So G has three components. Disconnected graph is split into, yeah. Okay, so now we can do number 14, which is to draw a connected graph with 8 vertices, a disconnected graph with 8 vertices and 2 components, and a disconnected graph with 8 vertices and 3 components. So I'll come around and give you whiteboard markers, and once you figure it out, put it up on the board. Because there's a lot, remember we talked about like the different options, there's a lot of ways to draw this. Anyway, goes like this. Let's see, did I get everybody? Yeah, I love the different ideas. Like there's so many graphs that we can draw. And so the idea for B it looks like for this one, we've now separated it into two squares instead of one all connecting. Or if we've got this house type graph and a path trailing down there. Now we've separated those. So or it's this and we break this edge, or this and we break this edge. And then for C, we can further do that. So like we have an edge here, and a long edge here with 1, 2, 3. I think there's another vertex in here. Yeah. Yeah, so you get the idea. So we break it into, there's different ways we can formulate these graphs where we break them into components. Great job. Okay, so how are we doing on time? We're going to 11:20. We're good so far. Okay, so we talked about walk, trail, and path. There's a special term for when a walk, trail, or path starts and ends at the same place. We call it closed. So a closed walk means it's a walk that starts and ends at the same vertex. So it starts and ends at the same vertex. It's just closed. Similarly, we can say a closed trail is similarly it's a trail that starts and ends at the same vertex. Where the trail definitions still apply, just now we have the notion for what it means to start and end at the same place. Just a note for these two, if it's not closed, implies it's open. And typically when we just say a trail, if we need to specify that for sure it doesn't start and end at the same place, then we would say it's an open trail or an open walk. It's a binary adjective. And then we have what we call a cycle. So we've got a walk, we've got a trail. What about a path? This idea of a closed path, we have a special term called a cycle, which is a the definition the book has is it's a closed walk such that the edges and immediate vertices are different. I don't know that I like the way that they phrase immediate vertices, but it's the idea that we start with a path which doesn't repeat vertices, doesn't repeat edges, and then we just draw an edge from the starting point to the ending point. Again, so like I said with walk and trail before, you don't necessarily see walk and trail a whole bunch, but you do see path and you do see cycle a lot. So understanding what a path is and what a cycle is really important. Okay, so got this graph again. Let's just reproduce it. Yes, edge goes here. Where this is the U, V, W, X, Y. Okay, so a closed walk, for example, is, let's see, what I have written down is V, Y, W, X, Y, Z, and V. So we start and end at the same place. And for this one, we started at V, and we go down to Y, and then up to W, down to X, back to Y, over to Z, up to V. So I guess this is also technically a trail too, because we didn't repeat any edges. Um, another closed trail, for example, is like ZZ. That's a closed trail. V, W, X, Y, V, V, W, X, Y, V. This is also a cycle where, here, let's highlight that one. V to W, W to X, X to Y, Y to V. Right? It's a cycle. We start and end at the same place, and we don't repeat edges, we don't repeat vertices. There's many cycles of length 3 in this graph. So length, again, being the number of edges. So U, V, and Z, that all forms a cycle. V, Z, and Y, V, W, and Y, W, X, and Y. Those are all cycles of length 3, which sometimes you'll hear called triangles. If we're writing a cycle like U, V, and Z, like this triangle here, you may have guessed it doesn't matter the order in which we wrote them. So it could be VZU or ZUV or ZVU. The order, unless we're working with a directed graph, the order that we write this down doesn't matter. It just, we start at one point, pick a direction, and follow that direction all the way around. So we wouldn't do like ZV and then ZU, like that doesn't make sense. We just list the vertices in either clockwise or counterclockwise order. Just pick one. So now I want to, we might, let's see. Have an activity, but I think I might save it. I might save it for the exam. I'll tell you what the activity is so that you can start thinking about it. I was thinking if we have vertices being the buildings on campus and the edges being there, you can walk directly from one to the other. So like maybe Galileo to Corth or Galileo to the chapel, you can walk directly from one to the other. But maybe to get to Garaventa from Galileo, you would need to go to like cross the street and go to Dante first, and then you get to Garaventa. That's the idea. And so the of choose the pairs and what's a walk, what's a trail between them. Where's there a cycle? That's the idea. Because we've got a lot of stuff to get through, so I'll leave that for the exam. You can start thinking about it. But I will do the packet problem, number 15. Or now that we know what it means for walk to be closed, how can we get these things from it? All right, any ideas? Closed walk that is not a closed trail. So a walk where, so if it's not a closed trail, then there's some edges that get repeated. Yeah.
But, U, X, W, V, U, W, X, U.
Okay. So we've got U to X, X to W, choosing one of those edges, W to V, V back to U, U to W, W to X again. So maybe, or I don't think it matters. So either one of those, because you go from X back to U and back on that edge that we've already looked at. Yeah, great. Any idea for a closed trail that is not a cycle? So something that repeats vertices. Yeah,
V, W, and X on one of them, then back to W and another, then U.
cool. V to W, W to X, X back to W, and then U and V. Yeah, so W gets repeated, but as long as we take one of the loops at a time, then that's a trail. So as long as both of the loops are used and not just one of them. Any ideas for the cycles? I'll hear just one of the options for each one of them. You give me a cycle of length 1. Yeah. Yeah. We just take that loop. Easy enough. Cycle of length 2. This is also possible because we have multiple edges. Yeah. Go from X to W and then back again. Which is technically a cycle because there's 2 distinct vertices and we take 2 distinct edges. Cycle of length 3. There's lots of options for this one. Someone else who didn't answer yet. X, U, W, X. X to U, W, back to X. Yeah. And then a cycle of length 4. It's just like this quadrilateral that we've got here, right? So like if we start at U, go to V, go to W, choose one of them, go back to U. So U, V, W, X, and U. That's a cycle of length 4. Okay. So we've got about 10 minutes left. So what I think I'm gonna do, we might go to, I'll talk about the definition and then we'll probably close out with packet 16. And then after that, there's a theorem that maybe we'll start next class by looking at. So there's 2 main pieces left in this chapter. One is regularity, the other is bipartite graphs. And so the idea for each of them is we'll say, what's the definition? And then we'll look at special cases of these that may be of interest. So first off, we'll say what it is. So a graph being regular means that all vertices have the same degree. So all vertices, if they have the same, if every vertex in the graph has the same degree, so our degree sequence is something like 2, 2, 2, 2, then the graph is regular. And additionally, whatever that number is, if we say it's R, then we say the graph is R regular. We just assign, so if we're talking about a general graph, then we will replace the number. So here R is 2, so we can say whatever this graph is, it's 2 regular, because all the degrees are 2. So let's look at some examples. This is a graph where all the degrees are the same. It's 0. R is 0, so we say it's 0 regular. Here's a graph where all the degrees are 1, so it's 1 regular. Now I've got a few different graphs for you. any cycle you get is going to be 2 regular. For all of these, treating these as distinct graphs, r equals 2. So they're 2 regular. And then giving you some more options here. We'll talk about this graph in a bit as well. Each of these vertices has 3 neighbors. So it's 3 regular. And then the book also has an r equals 4 regular, but I don't feel like drawing those at the moment. So I will refer you to the book if you want to see those. It's the same idea where one of them is what we call the complete graph on 5 vertices, where we've got 5 vertices and we draw all possible edges that assuming that it's a simple graph, we draw all possible edges. And the other one has 1, 2, 3, 4, 5, 6, 7 vertices, and it looks kind of cool. But yeah, the idea is where we draw a vertex, and each vertex has 4 neighbors. Every vertex has 4 neighbors. Let's end with a theorem. There's packet 16, but we'll maybe start with that next time. So theorem 2.2 in the book is we say let G be an R regular graph with n vertices. So the number of vertices is n, and we want to prove that G has n times r over 2 edges. So if we know that it has n vertices, then we want to show that the number of edges is n times r over 2. So to prove that, we know that G has n vertices. And each of those vertices has degree r. That's what follows from G being an R regular graph. So each with degree r. So we've got a lemma where we can sum all of the degrees and get something in terms of the number of edges. So if we sum all the degrees, that gives us, so the first vertex will be R, the second vertex will also be R, the third is R, and so on. And as we add these up, how many things of R are we adding? Well, it's all the vertices, so it's n. Yeah. So there's going to be n terms here, n things. And so the way we express that is n times r. And so by the handshaking lemma, we know that the sum of the degrees is equal to 2 times the vertices. And so to get our result, we just divide by 2 on both sides. So we get n times r over 2 equal to the number of edges. And we're done. That's the idea. So we use the handshaking lemma, something that we have proven, to help us prove this as well. So we've got 3 minutes, so maybe so 16, 17, and 18 are up next. Um, yeah, maybe spend the next 3 minutes like working on it. Working on 16 specifically. Then when you're done, you can leave and we'll start next time. Going over 16, 17, and 18. All right, 11:20. Thank you guys. I'll see you next time. Have a good Tuesday and Wednesday.